Have you ever wondered how your computer can possibly juggle playing music, running a web browser, and popping up a dozen notifications all at once without just collapsing? Well, the secret is something called CPU scheduling. And today, we're going to pull back the curtain and see exactly how it all works. Let's get into it.
So, let's start with a simple question to get our heads in the right space. Imagine you're running a super popular coffee shop, right? The line is out the door. But you've only got one espresso machine. How in the world do you decide who goes first? Do you help the person who's been waiting the longest? Or maybe the person who just wants a quick, simple order?
And believe it or not, that coffee shop problem, it's the perfect way to think about what your computer's operating system is dealing with thousands of times every single second. It is a constant, high-stakes balancing act.
See, in this analogy, all your open applications, your browser, your game, your music player, they're all the customers. In tech terms, we call them processes. And the barista, the one doing all the heavy lifting, that's your computer's central processing unit, the CPU. Lots of customers, but only one barista.
So, if the apps are the customers and the CPU is the barista, who's the manager? Who's the one telling the barista who to serve next? Well, that's the job of the operating system. It's the brains behind the whole operation, making sure every single process gets its turn.
And this whole process, this decision-making, it has an official name, CPU scheduling. It's literally how the operating system looks at that line of waiting programs, the ready queue, and picks one to give some time to the CPU. This is the magic that makes multitasking even possible.
Now, what's the point of all this? Well, the goal is really a three-way balancing act. You want to keep the CPU as busy as possible, you want to make sure programs aren't waiting around forever, and you have to be fair to everybody. The tricky part is, trying to do one of these things often makes the others harder.
Before a scheduler can even start making decisions, it has to make one massive, fundamental choice that defines everything it does. And that choice is, can it interrupt a task that's already running?
This choice splits scheduling into two big categories. On one side, you have preemptive scheduling. This is like our barista stopping a really complicated drink order to quickly pour an espresso for someone who just ran in. The other approach is non-preemptive. This is where once the barista starts an order, everyone else has to wait until it's completely finished. No interruptions allowed.
Okay, with that key distinction in mind, let's actually look at the playbook. What are the common strategies or algorithms that these schedulers actually use to manage that line?
The most straightforward strategy is called first come, first served, and it's exactly what it sounds like. You help customers in the precise order they showed up. It's a simple queue, just like lining up for a bus. The first process in line gets the CPU, and it keeps it until it's all done.
But, and this is a huge but, this simple method has a massive flaw called the convoy effect. Imagine you just ordered a simple black coffee, but you're stuck in line behind someone who ordered 50 different complicated lattes for their entire office. That tiny, quick task of yours is now forced to wait forever. That's the convoy effect, and it can bring everything to a crawl.
So while first come, first served is super easy to implement and it seems fair, it's often really inefficient. That convoy effect means the average wait time for everyone can get ridiculously long.
So how do you fix that digital traffic jam? Well, that leads us to our next strategy, shortest job first. You can think of this like the express lane at the grocery store. The scheduler looks at every process waiting in line and gives the CPU to the one it thinks will finish the fastest.
Now on paper, this is amazing. It's mathematically proven to give the best possible average waiting time, but it has two gigantic problems. First, how does the scheduler know how long a process is going to take? It basically has to predict the future, which is pretty much impossible to do perfectly. And second, what happens to a really long process? It could end up waiting forever if shorter and shorter jobs keep showing up, a problem we call starvation.
So all of this brings us to a really popular strategy that's built for fairness. It's called Round Robin. Instead of letting one process run until it's done, this strategy gives every single process in the queue a tiny slice of time with the CPU. This is really what makes the interactive systems we use every day feel so responsive.
The secret sauce here is something called a time quantum. It's a tiny, fixed slice of time. We're talking like 10 milliseconds. Each process gets to run for one quantum. If it's not finished, no problem. It just goes to the back of the line and waits for its next turn. It's like letting every customer use the coffee machine for exactly 1 minute. But that, of course, raises a really critical question. What is the perfect size for that time slice? What happens if you make it too small?
And here is the catch.
If that time quantum is absolutely tiny, the system spends more time switching between tasks than it does actually doing work. It's like a barista who spends more time calling out names and grabbing new cups than they do actually making coffee. This is called context switching overhead, and it can grind the entire system to a halt.
So, at the end of the day, Round Robin is fantastic for fairness and making a system feel snappy, but its performance is completely at the mercy of getting that time quantum size just right. That's why a lot of modern operating systems actually use more advanced schedulers that can change this quantum on the fly, trying to find that perfect sweet spot.
Okay, so I know this might all sound like pretty abstract computer science stuff, but choosing the right strategy has a massive direct impact on your daily life with technology.
The reason your phone feels so responsive and you can switch between apps so smoothly, that's because it's almost certainly using a preemptive round-robin style scheduler designed for exactly that. A giant server that's just crunching data in the background might use a totally different strategy. The wrong choice is what leads to lag, frustrating delays, and those moments where you're just staring at a spinning wheel.
So let's just do a quick recap. CPU scheduling is the hidden rulebook the OS uses to make your computer feel fast and fair. The simplest first-in, first-out idea sounds good, but it creates digital traffic jams. Picking the shortest job is technically the fastest, but it's like trying to predict the future, which isn't very practical. And finally, giving everyone a small slice of time is what ensures fairness and makes things feel responsive, which is why it's the go-to for the devices we use every day. You know, this whole idea is summed up perfectly by a key thought from our source material. Efficient CPU scheduling ensures fair allocation of resources, maximizes CPU usage, reduces waiting time, and enhances system responsiveness.
And all this leaves us with a really fascinating final question. As we move into a future with AI, self-driving cars, and billions of connected devices all demanding attention, that simple coffee shop problem gets way, way harder. In a world where some tasks are literally life or death and others are just background noise, what does the fairest or most efficient line even look like? That's the puzzle that engineers are trying to solve right now.